Have you ever paused and felt something strange about the world around you? A sense that reality might not be what it seems? That feeling, subtle as it is, has been at the heart of human inquiry for thousands of years. Philosophers have wrestled with it long before computers or simulations existed. Plato imagined shadows flickering on a cave wall and asked, "Are those shadows all we will ever know?" Descartes imagined a deceiving mind, crafting an illusory world around us. And today, we ask a new version of the same question. What if the universe itself is a simulation? Think about it. Every star, every mountain, every ocean, perfectly placed. Laws of nature operating with uncanny precision. Is it coincidence or design? This is not science fiction. It is a hypothesis, a framework that takes seriously the possibility that the universe we inhabit is not base reality, that it is generated, computed, rendered, like the most sophisticated of virtual worlds. What does this mean for us? It means everything we experience, our senses, our memories, the flow of time itself, could be outputs of rules we do not yet understand. And yet, the idea is humble and bold at the same time. Humble because it admits the limits of our knowledge. Bold because it allows the possibility that there exist systems or intelligences capable of constructing entire realities. Imagine for a moment, you are looking at the night sky. Each star might be a rendered point of light, calculated only when observed. The cosmos itself could be responding to perception, conserving resources, revealing only what is necessary. We start here, at the very edge of our understanding, asking a simple question. Could this all be constructed? Could the universe, with all its complexity, emerge from a set of rules, running on some unknown substrate? This is the question that drives simulation theory. Not fantasy, not paranoia, but curiosity. And it is a question worth following. Because even if the answer turns out to be no, the journey reveals the architecture of reality itself. It shows us how information, law, and observation intertwine to create the world we experience. So let us begin, step by step, not with answers, but with possibilities, and let the wonder guide us. Why would scientists even entertain the idea that the universe is a simulation? Because the universe behaves in ways that feel almost coded. Look around. From the largest galaxy clusters to the smallest quantum particles, patterns emerge. The laws of physics are precise. Maxwell's equations, Newton's gravitation, Einstein's relativity, all operate with astonishing regularity. Slightly tweak a constant, the speed of light, Planck's constant, the strength of gravity, and the cosmos we know could not exist. Some call this fine-tuning. Others see it as evidence of something deeper. Perhaps the universe is efficient. Perhaps it is engineered with rules that create complexity from simplicity. Consider quantum mechanics. Particles exist in multiple states until observed. A wave of probabilities collapses into a definite outcome the moment it is measured. It's as if the universe waits for attention, rendering only what is observed. Like a computer game where parts of the world are drawn only when the player is nearby. Then there's information itself. Modern physics treats information as physical. Black holes, for example, store massive amounts of data. Virtual particles pop in and out of existence in empty space. Reality may, at its core, be information. And if it is, then simulating it becomes theoretically possible. Even more striking, simple rules can produce astonishing complexity. Cellular automata, fractals, and algorithmic systems in our computers generate intricate patterns from minimal input. Could the universe operate the same way? Could the cosmos itself emerge from rules iterated across space and time, producing the richness we see? Some argue this is speculative, but here's the key. Simulation theory is not fantasy, it's hypothesis-driven. It asks, if the universe were computed, what would we expect to see? Compact laws, emergent structures, patterns, and efficiency. And, remarkably, that is exactly what we observe. We can even take it further. Quantum phenomena, like entanglement, suggest that information is distributed non-locally. Reality may not be a fixed stage, but a network of correlations. A simulation would naturally use similar strategies. Compute interactions where needed, store information efficiently, avoid redundancy. So, the scientific and mathematical foundations are not just metaphors. They are evidence that the universe could, in principle, be a computational system. From elegant equations to quantum surprises, from information storage to emergent complexity, the signs align in a way that invites serious contemplation. In short, science doesn't dismiss the idea. It frames it, tests its limits, and asks, what would a simulated universe look like? And how could we know? And this question brings us closer to the heart of the theory. Not just speculation, but observation. Because if clues exist, they are hidden in the very structure of reality itself. If the universe is a simulation, could there be hints? Clues hidden in the fabric of reality itself? Let's explore some possibilities. First, consider the Planck scale. Physics identifies the smallest measurable units of length and time, the Planck length and Planck time. Could these be the universe's pixels? If reality is computed, there might be a minimum resolution, a point beyond which detail cannot exist. Like a digital image, finely detailed but ultimately discrete. Next, the fine-tuning of constants. Gravity, the strength of electromagnetism, the masses of fundamental particles, all precisely balanced. Slight changes, and stars wouldn't form, chemistry wouldn't exist, life would be impossible. Could this be chance? Or is it a set of parameters intentionally calibrated? In a simulation, constants could be configurable settings designed to produce a coherent, complex world. Then, black holes. They are not just destructive, they are information vaults. The holographic principle suggests that the information content of a volume of space can be encoded on its boundary. That's remarkably similar to how computers store and compress data. It's as if the universe itself optimizes storage and processing, a clue that a computational substrate might be at work. Look also at patterns and regularities. Fractals, scale invariance, and symmetry appear everywhere, from galaxies to crystals, from turbulence to snowflakes. Simple rules can generate astonishing complexity. Emergence from minimal input is exactly how efficient systems, both natural and artificial, operate. Finally, there's the observer effect. Quantum mechanics tells us that particles exist in multiple states until measured. Could the universe render reality only where it interacts with consciousness? A simulation would naturally economize, focusing computational power where it matters most, on active observation. None of these clues are definitive, but together they form a pattern. A web of anomalies and consistencies that invites serious thought. They are not just curiosities, they are testable, measurable features of the cosmos that could, in principle, reveal the architecture behind reality. This is where science and imagination meet. Each clue is an invitation to look closer, to question assumptions, and to explore with rigor. Simulation theory thrives not on untested speculation, but on disciplined observation. So, As you gaze at the stars tonight, consider this. The universe may contain messages in its structure, subtle signals, hints of design, or the fingerprints of the rules that generate it. And if so, what we see is only the surface, the rendered layer of something far more profound. So, if the universe is a simulation, what might that world look like? First, consider the structure. It may be hierarchical, a base reality running nested simulations. One layer could host countless simulated worlds. If so, most observers, including us, might inhabit a simulated branch rather than the base reality. This is a statistical argument, simple yet profound. Typical consciousness may exist inside a simulated environment. Another possibility is distributed computation. Reality could be updated continuously by a vast network, processing states in parallel across space and time. It might not be computers as we know them, but a system that behaves computationally, efficiently distributing and compressing information. Black holes and horizon physics hint that nature may already implement similar strategies. Then, consider rule-based emergence. Simple rules iterated over enormous scales can produce astonishing complexity. Think cellular automata, minimal instructions, infinite variety. Life, consciousness, galaxies, all emerging naturally from foundational rules. A simulated universe might operate on similar principles, where the appearance of depth and complexity arises from compact, elegant algorithms. What about fidelity? A simulated universe may render reality selectively. Only regions of high interaction, those observed closely, are fully detailed. Distant or unobserved areas might exist only probabilistically. Like a video game world, computational resources are concentrated where needed. Could we detect signs? Perhaps subtle discontinuities in energy distributions, constraints on cosmic rays, or pixelated patterns at extreme scales. We might even find compressibility in the laws themselves, hinting at underlying code. While speculative, these are testable avenues. Simulation theory, unlike pure fantasy, encourages empirical exploration. And yet, the beauty of this theory lies not in proving it immediately, but in reframing how we think about reality. It challenges assumptions, stretches imagination, and sharpens observation. Whether or not we inhabit a simulated cosmos, studying the possibility deepens our understanding of information, computation, and the architecture of existence itself. So, as you finish this thought, consider the extraordinary. Every star, every wave, every breath may be part of a complex rendered reality, a system more sophisticated than anything we can yet imagine. The universe, perhaps, is a masterpiece of computation.